Welcome back, Physics 30. This is the third installment in the CO1 unit. This is CO1.3, Kinetic Energy and the WorkEnergy Principle. So we've looked at the definition of work from the physics sense, a force being applied on an object that's undergoing a displacement. And that first part we looked at whether it's a constant force. Then CO1.2 we looked at, well, what happens if the force changes? And that's where the force versus displacement graph comes into play in calculating the areas. Now we look at kinetic energy and how that applies to work. So define and calculate the kinetic energy of a moving object, explain what is meant by the work energy principle, and solve problems involving the work energy principle. So energy in the physics sense is the ability to do work. This simple definition is valid for mechanical energy, which will be discussed later in this section. A moving object can do work on another object it strikes. A flying cannonball does work on a brick wall when it knocks it down. A moving hammer does work on a nail because it drives it into the wood. In either case, a moving object exerts a force on a second object which undergoes a displacement. So force, displacement, so of course work is equal to F multiplied by D. An object in motion has the ability to do work and is therefore said to have energy. So if you have the ability to do work, there must be some energy involved. The energy of motion, and if you look there, the word kinetic implies moving, is called kinetic energy. Energy due to movement. And it depends on a few things. It depends upon the mass of an object, as you can see, and it depends how fast it's moving. So if you have a small mass moving with a very large velocity, its energy is going to be relatively high. Or a very massive object moving with a low velocity, it's still going to have a high energy. So as these variables increase, kinetic energy increases as well. Okay, so we look at determine the kinetic energy of a 145 kg baseball moving at 13.5 meters per second. Quite easily done. So we have the mass. Now, mass is 145 grams, but as you can see here, mass has to be in kilograms. So divided by 1,000, 0.145 kgs, because there's 1,000 grams in a kilogram. The V, 13.5 meters per second. And kinetic energy, E symbolized by EK, kinetic energy, is the question mark. So EK equals 1/2 mv squared. So 1/2 of the mass in kilograms multiplied by the velocity squared. Now, of course, bed mass, you have to use exponents comes before multiplying. So make sure you do that. 13.213 joules. And if we round that off to 3 sig figs, that's 13.2 joules. Okay, if we look at the next page, the work done on an object is equal to the energy gained by the object. So the work done is equal to the energy that it has gained. This is known as the work energy principle. This is the key part right here. Work done is equal to a change in energy that it experiences. So we could, before we do this, we could say EK final minus EK initial. W equals change in kinetic energy. And of course, a change in anything is some final amount minus an initial amount. So EK final is this 1/2 mv final squared. EK initial, 1/2 mv initial squared. So that's the key thing. The work done on something is going to result in a change in energy, or a change in energy of an object is going to equal to work done, as we'll see down here in the hammer example. The work energy principle is very useful reformulation of Newton's laws. It tells that if positive work is done on an object, the total kinetic energy increase. So if we have positive work, kinetic energy increases by that amount. The principle also holds true for the reverse. If the work done on an object is negative, and we'll see that in a bit, the kinetic energy decreases by that amount. So if you're gaining energy, positive work. Losing energy, negative work. That is, a net force exerted on an object opposite to an object's direction of motion increases its speed and its kinetic energy. An example is a moving hammer striking a nail. The net force on the hammer would be negative F. So let's take a look at that for a second. So if we look back in Newton's third law, of course, we always look at the action here. We look at the hammer coming down and driving the nail into the wood. So this is the, right here, that is the action force. Hammer hits nail into wood. Action force. So hammer hits nail forward. The reaction is nail hits hammer backwards. Reaction. So as soon as that hammer hits that nail, that hammer, if I just look at what's happening to the hammer is going to experience a negative force. And you can feel that when you use a hammer. You can feel the force of the nail going back on the hammer. So that is a negative force, because if we take a look here, the hammer is going this way, but the force on the hammer is this way. So if we recall in the very first section, that's a 180 degrees. So if we used our old equation here, FD cos theta, the force and the displacement are 180. And if you remember pre-calc 30, the cos of the cos of 180 is negative 1. So negative 1 times F times D, negative FD. So we get a negative answer here, and that just simply means that it's negative work. The work done is causing a decrease in energy. So the work done on the hammer is negative. So that results in the hammer's moving energy of movement, decreasing. If it was positive, increasing. The hammer, as it slows down, still does positive work on the nail, though, because if we look at the nail is going to be going this way, and the hammer hit it in that same direction. So notice the F and D are in the same direction. So cos of theta, or cos of 0 is going to be 1. So it's just simply W is equal to F times D, because cos of 0 is 1, and we get that. So and here's the key thing. So what the hammer is losing, the decrease in kinetic energy of the hammer is equal to the work the hammer could do on another object. So the hammer is losing the energy, but the nail is gaining it. So the work done on the nail work is positive, and its energy is going to increase. So that's a key thing to know. Looking at the two separate objects there, it's easy to see the action force, to see what's happening on the nail, but something is also happening on the hammer. It's losing energy, which is going to be resulting in that transfer of energy to the nail. The change in kinetic energy is directly proportional to the mass of the object. It's also proportional to the square of the speed, because remember it was 1/2 mv squared. Thus, if the mass is doubled, kinetic energy is doubled. So if this gets 2 times bigger, this gets 2 times bigger. But if this gets 2 times bigger, 2 squared is 4. EK gets 4 times bigger because it's a squared relationship. Okay, if you look at the third page, since there's a direct connection between work and kinetic energy, energy is measured in the same unit as work. Joules. Like work, kinetic energy is a scalar quantity. It has a size but not a direction. If we're talking about positive and negative in terms of energy or work, that just means gain or loss. Let's look at this. How much net work is required to accelerate a 1,000 kg car from 20 meters per second to 30 meters per second? So how the net work, so we could say work is equal to force times displacement, but we don't know anything about force. We don't know anything about displacement. We know the mass. We know a velocity change. So that is kinetic energy there. If a moving object is getting faster, that is a change in energy. So in our case, we talked about work is equal to a change in energy. In this case, that energy is kinetic. So we have final kinetic energy minus initial kinetic energy. And of course, we can state that as 1/2 mv final squared minus 1/2 mv initial squared. So it's a 1000 kg car. It was originally moving at 20, and I'm going to make it like that here. And it went to 30. So it's 450,000 minus 200,000. That's going to give us 250,000. And if I look back here, technically there was only one sig fig there. So if we take a look there, 300,000 joules. Okay, it's because they've given the masses, or mass, and the initial velocity was 20 meters per second, and the final velocity was 30 meters per second. So we can see it's a kinetic energy change. A change in velocity is going to be a kinetic energy change, and work is a change in energy. So if we know the type of energy here, we can figure out work. Okay, I think we'll stop the video there. We'll do part 2, in which we'll do the last example and bring everything to an end.